In this video, I'm going to tell you about RC circuits. Let me start by diagramming the simplest kind of an RC circuit. It has a battery or some source of constant EMF, a resistor, and a capacitor. And the presence of the R and the C in this circuit is where the name RC circuit comes from. The switch is used to open and close the circuit, which determines whether the current can flow or not. Let's imagine for a moment that the capacitor in this circuit is initially uncharged, and then the switch is closed, allowing current to flow. Notice that this will result in charge building up on the capacitor. What do you imagine the current in the circuit and the charge on the capacitor will look like as a function of time? Take a moment to make some predictions about what will happen, and if you need some extra time, just pause the video for as long as you need to. Now I'm going to set up a real RC circuit so you can see if your prediction is correct. I have everything I need right here on the table. The gray box in the back is a power supply. This will be the source of EMF for the circuit, and I have it set to deliver a constant 9 volts when the switch is flipped. The next component of the circuit is a light bulb, which serves as my resistor. The big metal cylinder is a capacitor. The wire from the capacitor needs to go back to the power supply to complete the circuit, and then I need to plug in the power supply. The switch for the power supply is back behind the capacitor, and when I flip that switch, it will set up a constant EMF in the circuit. But first I want to turn off the lights. You can see now that my hand is ready to flip the switch, but focus on the light bulb and watch what happens to it. Let me show you that again. As you can see, the light bulb lights up immediately, and it gradually dims until it goes out altogether. This shows that current flows immediately and decreases over time. Meanwhile, the current can't pass through the capacitor, so as current is flowing in the circuit, the capacitor must be getting charged. The charge should be increasing quickly at first, and then reach some maximum charge when the current stops flowing. By the way, in case you're not convinced that charge is stored on the capacitor, you can remove the power supply from the circuit altogether. When you take these leads off and connect them directly together, you can see what happens. Notice how the light bulb lights up and dims again. This shows that there was indeed charge stored on the capacitor. Now that you have a conceptual sense of what should be happening in the circuit, let's derive equations for the charge on the capacitor and the current in the circuit as a function of time. Remember that Kirchhoff's loop rule says that the sum of the potential increases and drops around the circuit is equal to 0. Another way of saying this is that delta V equals 0. I'm going to choose this loop and starting with the EMF, apply delta V. That gives me EMF minus IR minus Q over C is equal to 0. Now remember that current in the circuit is defined as dQ by dt, and this dQ by dt is also the rate at which charge is being loaded onto the capacitor. Making the substitution for current, I'm left with EMF minus dQ by dt times R minus Q over C is equal to 0. And from your calculus studies, you'll perhaps recognize this as a separable differential equation. That's the physics, and from here I'm going to use calculus to solve this equation for charge on the capacitor and current in the circuit as a function of time. The first thing I'm going to do is clean up a bit by moving dQ by dt times R over to the right-hand side of the equation, and I'm also going to multiply through by C. On the left-hand side, that'll leave me with CE minus Q. Then I'll put dt over RC on the left-hand side and collect dQ over CE minus Q on the right. The variables are now separated, and I can add some integral signs, remembering that because these are indefinite integrals, I'll need to include a constant term. I'm avoiding using the label C for constant because I've already used it for capacitance. Integrating both sides gives T over RC is equal to ln of CE minus Q multiplied by -1 because of the chain rule, plus a constant. And now to find the constant term. When T equals 0, the charge on the capacitor is equal to 0. And that means that 0 is equal to ln of CE minus 0 times -1 plus a constant. And that tells us that the constant is equal to ln of CE. So I'll make that substitution back into the equation and find that T over RC is equal to ln of CE minus Q, negative, plus ln of CE. Now I'm going to multiply through by -1 just because, and then I'm going to combine the log terms. That gives me negative T over RC is equal to ln of CE minus Q divided by CE. Now I can exponentiate both sides, giving me e to the minus T over RC is equal to CE minus Q over CE. And then it's just a matter of doing a little bit of algebra to get Q is equal to CE times 1 minus e to the minus T over RC. I'm going to put a box around that one because that's an important equation. Now we can get current pretty easily by remembering that current is equal to dq by dt, and taking the derivative, we find that current is equal to E over R times e to the minus T over RC. And I'll put a box around that one as well. Okay, now that we have these equations worked out, let's take a look at some graphs. The plot of Q starts out at 0 and gradually approaches a horizontal asymptote at CE. Meanwhile, the current in the circuit starts off at E over R and gradually approaches 0. Think back to the video of the RC circuit and check that these plots are consistent with what you saw. It's often useful to get a sense of how quickly the capacitor is charging, and for that we define a new term called the time constant. The symbol for the time constant is tau, and this quantity is defined as RC. Let's use the derived equations to calculate Q and I at one time constant. Q will be equal to CE times 1 minus e to the minus RC over RC. But that's just CE times 1 minus e to the minus 1. And e to the minus 1 is 0.37, so this is 0.63 times CE. Remember that CE is the final charge on the capacitor, so at one time constant, the capacitor is 63% charged. I is equal to E over R times e to the minus RC over RC, but that's E over R times e to the minus 1, and that's 0.37 E over R. And remember that the initial current was E over R, so at one time constant, the current has decayed to 37% of the original current. I'll label tau on the plots. It is pretty cool to note that the time constant depends upon R and C only, not on the value of the EMF. So you can supply a higher voltage to the circuit, but the time it takes the current to decay and the charge to build up will remain the same. If you want to change the time constant, you need to change R or C. And if this movie weren't already too long, I'd show you how connecting a second identical capacitor in series makes the light bulb turn off much faster. So for the simple RC circuit, we've derived equations that describe the current in the circuit and the charge on the capacitor during charging. During the demonstration, I also unhooked the power supply and discharged the capacitor through the light bulb. If you'd like to derive the equations for the discharging RC circuit, you can check out the next video.